Now let us see what we mean by coherence. Okay, as I said in the last section, in practice, amplitude and phase of two waves vary randomly in time. And again, therefore they are not completely coherent, and also they are not monochromatic and constant in amplitude. They will keep changing. They are not completely coherent, they are not monochromatic, and constant in amplitude. Okay, this is the realistic situation, and therefore we define something called partial coherence and the degree of partial coherence, or how far these two waves can be correlated. That is the subject of this class. And also light flux at a given point fluctuates rapidly, and therefore when you talk about intensity, you talk about time averaged intensity. Time averaged intensity. Okay. Usually you can define or you represent a time averaged intensity with this sort of brackets, these two triangular brackets. And if you do that, this is what you get. You get a time average value of this thing. And by time averaging, we define it like if you, for a function f, it is limit t tends to infinity. So for you take larger and larger periods, t is capital T is the period, and this is how you define. You average over or integrate over one period, 0 to t, and then this is your time averaged value. Again, not very strict assumptions you make. I mean, okay, it's a common assumption. Here we make two assumptions. The time average is independent of choice of origin of time, and also, which means all these things are stationary. All the quantities that you consider are stationary. They have then optical fields have same polarization. You take only one direction. Otherwise, then you will have something like a polarization vector for each polarization unit vector for each one. It could be a combination of I, E, X plus J, E, Y, etc. And you want to avoid that. That's why we take only one polarization, and therefore we can take the magnitudes without considering the vectorial nature of this one. Okay, given that, you can write equation 1 is like this. Equation 1 was this one. Intensity, okay, this we have seen in the last section. I is equal to I1 plus I2 plus this quantity. Okay, remember this time it is time average, and that is your interval. Now consider a situation. Here, this is your all familiar Young's double slit experiment. Here, in Young's double slit experiments, you have two sources, S1 here. Here you have S2, and the light coming out from here will interfere at some point, let's say R, from your screen. Then you have the Y coordinate here, and these two sources are derived from the same source. Yes, at some point. And this will result in the interference pattern. That is normally the case for all interference experiments. As you have seen in the Michelson interferometer in the last section, it was also derived from the same source. You have two beams derived from the same source. Okay, that is your situation, and you consider this situation now. Then E1 and E2, that is the wave trains coming from here E2. Here you have the electric fields like E1. Then when they come at this point here or this point here or this point here, they differ. E1 and E2 differ in optical paths. You can represent the situation like you have the same source here. Okay, these are your derived sources. Then this is your observation point, and this path here is path 2, this path here is path 1, and they differ optical path length. Okay, in this picture also you can see I have drawn it in such a way that there are different paths. And if you take t as the time taken for light along path 1, okay, it takes some time to go to the slit 1 or source 1, then it takes some time to reach this one. This is the total time is t. Now, because they are out of phase, the second guy must be coming at a different interval. That t is different by a constant tau. And in that case, I'm going to write this second term here, this term in the interference intensity distribution as it's like this one, where it is simply a replacement for this one. Okay, E1 t plus E2 t plus tau. Okay, they are different in phase. And also maybe there are differences in amplitude, that's why I don't keep the same amplitude here. And this function here, as defined by this equation, is called the mutual coherence function or correlation function. It correlates E1 and a time delayed or phase delayed E2, and that is defined as the mutual coherence function or correlation function. You will see that this correlation function in many branches of physics, like signal processing, for example. You delay one pulse with respect to the other, and then you try to see what is common between them. You keep changing this delay tau, and you change these tau in steps, which means that with one pulse, if you keep E1 as E1 is stationary, you don't do anything, then you change the second one. That's what we do when you do with the microscope interferometer. You keep one of the mirrors constant and you keep changing the other one. This is fixed. But while doing that, you change the phase relative to, okay, if this is E1, if you take this as E1, if you take this as E2, then you change the relative delay, means you change the phase between them. And that function is, you should remember the definition of the correlation function. And you can do it with the same function. Okay, here 1, 1 instead of 1, 2 in here. Here you are comparing the function with itself. In that case, uh, you call it autocorrelation. When you compare the function, you take one electric field amplitude, take a replica of the electric field amplitude, then you try to overlap them and try to see what is happening, what is in there. This is a situation where that we will use in optics lab while we try to measure very short optical pulses, femtosecond laser pulses. That is
Note the form. This mathematics climate എന്ന് നിർത്തില്ല സാർ അപ്പോൾ ഇത് ഫോം ആയി പോകാൻ അപ്ഡേറ്റ് ചെയ്യണം സോ ഈ മാത്തമെറ്റിക്സ് ഫോം എഴുതണം ഇങ്ങനെ കൊടുക്കാം.
okay, and is called autocorrelation or self-coherence function. Okay, the common names for the mutual coherence function is used in optics and in the situation where you have interference, but this is also the correlation function or cross correlation function. These terms you will encounter more often in many branches of physics. And in this case, it is this autocorrelation function that you will see very often compared to self-coherence function. That is a terminology that is commonly used. And gamma 11 therefore is intensity I1. Gamma 22 is intensity I2. From here you can see that. Then you can, with these two in mind, you can define a normalized correlation function, which is also called the degree of partial coherence, and that can be defined as gamma 12 is gamma 12 of the mutual coherence function or correlation function divided by the autocorrelation function, square root of this. Okay, that is definition. You find the proper method for normalization here, and that is this small gamma 12, which is called the degree of partial coherence, is defined as the mutual coherence function divided by our correlation function divided by the normalization factors, the autocorrelation functions, and that is I1, square root of I1, that is a degree of partial coherence. Okay, there are some uses for this one. And therefore, the intensity at the point of superposition can be like this. Okay, here we have, okay, what was your previous equation? This equation was, okay, here I1 plus I2 plus 2 of this one here. Now we have, since we are using the normalized quantity, you have this factor square root of y times the small gamma, degree of partial coherence. Okay, what was your starting point? You had a partially coherent, not very strictly monochromatic source, because you had of slightly different wavelength represented by K1 and K2. These were the two propagation vectors, and you arrive at this. And again, this gamma 12 is a complex periodic function of tau, the time delay between the two phases. And how did that happen? Because we started from the value of theta. theta. Theta was k1 dot r minus k2 dot r plus phi 1 minus, and this is the when you try to change uh, tau, you change this value here. You change the relative phase difference between the two, or you change the optical path length between the two waves, and therefore you change the value of theta, and therefore this complex amplitude here is a function of theta, and therefore it's a function of tau. And if this is 0, the degree of partial coherence is 0, means there is no interference. Because this term becomes 0, the intensity at the point of interest, superposition, is I equal to simply addition of the two intensities. There is no interference. Because there is no phase correlation between the two. And if gamma 1, 2 is non-zero, means you have some degree of interference between the two, or you have the intensity redistribution at the superposition plane. Now, if gamma 1, 2 is 1, this is complete coherence between the two, and if it is 0, or that is again is complete constructive interference, or total constructive interference that we have seen in the last section. This is complete incoherence, and where there is no interference. And this is the situation that we normally encounter, where this gamma, small gamma 1, 2, or the degree of partial coherence is between 0 and 1, and that is what we call partial coherence. And therefore, in a pattern of interference, the intensity varies between the maximum value, which is I1 plus I2 plus 2 square root of I1 I2 gamma 1 2, where this is the magnitude of the degree of partial coherence, and also when the minimum value is when then this becomes minus 1, because the phase part, cos theta part, becomes minus 1. And therefore you can define something called fringe visibility, I max minus I minimum divided by the I max plus I minimum. That is how you define the fringe visibility, and that is therefore, if you substitute for I max and I minimum, 2 square root of I1 I2 gamma 2 plus divided by I1 plus I2. This will give you the fringe visibility. Also, fringe visibility is determined by gamma 1 2. And what happens if you have the same intensity for the two beams, where I1 plus I2, as we have seen last time, let's say I0, then the fringe visibility becomes the magnitude of the what? The degree of partial coherence, or they become both the same. Fringe visibility in this special case, which is normally, which is not very unusual in the case of interference, light interference. The fringe visibility is nothing but degree of partial coherence. Or you can even measure that in that sense. If you use a CCD, you can measure the fringe visibility, and that will give you, and if both the intensities are more or less equal, that will give you the degree of partial coherence. And for complete coherence, gamma 1 2 is 1, and therefore visibility is 1. That is maximum contrast. And complete incoherence means the visibility is 0, which means there is no interference or there is no fringes. Okay, that is what I wanted to tell you today. And I think we have a little bit more time. Okay, let's see what we have seen. This is what we have seen is the, to start with, we looked at the principle of linear superposition. Then it is the vectorial addition of electric field. What we do is in an interference experiment, okay, suppose you see the interference fringes. Then at the superposition plane, okay, you have two sources. Then you have a plane where you look for interference. You try to superpose the waves that is coming out from these two sources, and you try to see the intensity redistribution at this point, where we add the intensities. The electric field amplitudes. Okay, and you can, as I said, it is the same for the magnetic field also associated with the electromagnetic wave. Then you consider the plane harmonic waves with the constant phase difference between them. Otherwise, there is no difference whether you add the intensities or the amplitudes. If there is no phase correlation between the two waves, this term here becomes 0, and what you end up with is simply adding the intensity. It is not more than you have two flash lamps, then you shine them onto the same spot, then you will see, if you do it one by one, you will see an intensity addition. There is no other intensity redistribution on the screen. And because there is no phase correlations between the two waves. On average, on time averaged, there is no time average phase correlations between the two. There could be one or two or many of these things happen, but since they are varying randomly, the phases, there is no real intensity redistribution as given by this term in the equation here. Okay, and then we consider the special cases: total constructive interference, destructive interference, and total destructive interference. Then you consider a special case where the maximum intensity, if you keep the intensities of the two beams constant and equal, the intensity at the bright fringe maximum, okay, if you have dark and bright fringes like this, okay, this is a dark fringe, it's a bright fringe, dark fringe, so it doesn't have to be linear, okay, it can be circular fringes. Then intensity at point at the center of the bright fringe, the maximum intensity will be 4 times the initial intensity. And at the minimum, you should have complete darkness, which means I minimum, the intensity at that point, the center of the bright fringe center of the dark fringe should be completely dark. And there are certain conditions. They must have nearly the same frequency. Only then you can keep that constant phase difference. And white light do form interference fringes in different colors. White light fringes, if you look at them, they are colored, and, which means that only the waves that have more or less the same frequency can interfere with each other. Then, for the best possible fringe pattern or maximum contrast, you keep both the amplitudes or intensities of both beams equal. And you can, the two sources must maintain a constant phase difference, whether it is it is derived from the same source, or if they are two different sources, but they should be phase locked. These two waves must be phase locked to see interference fringes. And that was it about the section 1. Then we had the theory of partial coherence. This is applicable in most of the real life situations where the amplitude, the waves are not completely coherent. They are coherent for a certain length of time and over a certain region of space. Then they are not strictly monochromatic, and they don't have the strictly the same amplitude, constant amplitude, and therefore you define something called the degree of partial coherence. That is what we have done in this section, and for that we use, because these things are varying in time, we use time average values of this one, and you define time average like this one, which we may use in coming classes. Then here you make two assumptions. Okay, this is not very. Okay, they have the same polarization. All the time average is independent of choice of time. And equation 1. Okay, this is your interference equation. Now I do justify two sources. Then you consider two sources derived from the same source, and you have an optical delay of tau between them. Then you consider this time. From there, you define a mutual coherence function or correlation function, and this function can be used to correlate one wave with itself, or one wave train with itself, and therefore that is called autocorrelation function. And you can define the autocorrelation, you can use the autocorrelation functions. They are nothing but the intensities of the waves to normalize the mutual coherence function or correlation function, and that is you define something else called the degree of partial coherence, and that can be defined as the normalized mutual coherence function, and that is how we can finally write the intensity equation I at the point of observation, that is from two sources. You have a screen at the end, these are your two sources, and the intensity distribution at the observation point can be written as I1 plus I2 plus 2 square root of I1 I2 and the real part of this one. Again, if you simplify that, you can write something like this. That is the maximum minimum value of at the point of, or the plane of observation, and from there you can have the fringe visibility defined like this one: I max minus I minimum, I plus I max plus I minimum. That is what it is. and it is related to gamma 1 2 or the degree of partial coherence. And therefore, in the special case of the both the beams being constant in intensity, you can have the fringe visibility as the degree of partial coherence or the magnitude of degree of partial coherence. And we call, if complete coherence means gamma 1 2 is 1, complete incoherence means this is this, and therefore the fringe visibility becomes 0 in this case, 1 in this case, and therefore maximum contrast, there are no fringes in this case of complete incoherence. Learn uh, principle of superposition, degree of partial coherence, mutual coherence function, autocorrelation function, uh, and fringe visibility. From there. Okay, with that, maybe we can stop for today.